this is a 3D model of all the pneumatic pumping components that we're using for this design. Here, you can see the air preparation unit connected to an air compressor, the compressor being the first object in blue. The air compressor provides a minimum pressure of 100 psi and supplies that compressed air to the air preparation unit, which has a filter and a regulator as a part of it. The filter ensures that there are no impurities in the air that we're trying to pass on to the solenoid valve, as moisture and dust can tend to damage the solenoid or the 5-2 valve. That can be seen right here. The pressure regulator allows us to increase or decrease the pressurized air, which is being delivered to the cylinder ultimately. And ideally, we would also like to have a sensor that detects whether the desired amount of or the desired pressure of air is being released or not. If for some reason we're not getting the desired air pressure, we could tag that as a failure scenario and try to debug if the air compressor was turned on and working correctly, if the air compressor and the air preparation unit are connected and you're getting some compressed air into the unit. If that is a scenario, we could check if the filter has been clogged, if there's any cloggings, the auto drain, or we could check if the pressure regulator for some reason is not working as desired, or the other scenario would be that the pressure sensor itself is defective. However, we had to drop the pressure sensor for the purpose of this project because it was getting a little too expensive for us for now. But that is something that we would definitely like to have in our future designs if feasible. Here we see the 5-2 or the solenoid valve. It's a single coil component, and it gets connected to the cylinder, which has a piston on it via tubes. Now the placement of the cylinder over here is just as a frame of reference. The cylinder will actually be situated a little further away from the rest of the components. That is how we afford semi-portableness. No matter where in the ambulance the patient is located, we can make sure that our adjustable arm over here, it is a little bit unclear that this can vary in length. The easiest way of visualizing it would be something like a mic stand. So this can be of variable length. It can be elongated if the patient is further away, or we can make sure that the BVM is very close to the patient's mouth, because usually, and this is the information that we got from our stakeholders, the BVM is hardly 1.5 feet away from the person's mouth in either of the scenarios where they have a mask on their faces or an endotracheal intubation. So on the arm, we have a C-clasp that holds the BVM in place. And we have another C-shaft, sort of a structure, which has a joint over here. And that has the cylinder mounted on it. The cylinder itself has a curved metallic element added to the end of the piston, such that the curvature ensures that when we're pumping the bag constantly, we're not tearing the bag at any point. Instead of a square block, we chose the curved one to ensure that we were not, due to excessive force or for any other reason, damaging the bag. Here we see a better and a more refined structure of the arm. This is what the arm is going to look like when there is no patient, or if the BVM is not being used for a particular patient in transport. Right here we have the C-clasp that gets that can be made stable, or that can be made immovable by just adding a tiny little pin over here. And once the pin is removed, it can come down, as was seen in the previous image. So this pin ensures that during transport, the C-clasp itself is not wobbly or not getting displaced or accidentally injuring anyone. One of the reasons why we decided on facilitating or affording this sort of a motion is because the length of the arm plus the C shaft could get as long as 3.5 feet when in transport, and when it is required, that's a completely acceptable measurement because the ambulance on the inside is about 6 feet wide. So that affords space to do other activity as well. But when it is not needed, this entire structure, if the C-class is bent in this fashion, comes out to be 1.5 feet or 2 at the most in length, instead of the 3.5 feet that it was previously. So as you can see, this is our cylinder. It is held on to the C shaft by this panel right here. And this is the C clasp that our BVM can easily be attached to or detached from without any or excessive discomfort to the patient. This is another image where we see the patient lying down, and when the patient is using the BVM in this structure, when the patient is brought into the ambulance, the BVM can be attached here quite easily without, again, discomfort to the patient, and the BVM can reside on the person's face, and the piston, since the C-clasp was brought down, it was the pin that you saw earlier, which was over here in the previous image, was brought and locked in here, so that again, during motion, the clasp is not flailing around or is not getting out of the way or injuring anyone. So this pin over here is going to ensure that it is locked in place. The movement of the piston is going to be in the direction or on the axis of the arm itself, allowing better performance. And over here, we see the cylinder with the curved piston that we talked about previously. And yeah, this is affording a similar sort of a setup that manual pumping does, because usually when the BVM is being pumped manually, the bag is quite close to the patient's face. And one of the attendants, either the nurses or the paramedics, or even sometimes the relatives, have to go in and squeeze the bag manually close to the person's face, but this is just optimizing that task. That was all for our alpha design. We're going to implement, we're going to be getting all the components in shortly, and we will be implementing this design for our beta release. So we will be doing more excessive testing, and we're going to check all the criterias, all the requirement criterias, and if this design fulfills them all. Thank you so much.